Hi, Shruti. Yes.
Hi everyone. I'm Shruti. I work in the TF-RMM team. So I'll be talking about how we are using CPP check for MISRA compliance in the RMM. So CPP check is an open source free tool. It's a static analyzer and it can detect all various kind of bugs like undefined behavior and security vulnerabilities. And it also has a add-on to check coding safety guideline standards like MISRA and CertC. So our goal is to integrate CPP check in our in our build system so that all external contributors can run CPP check without having to worry about license and uh, which yeah. Uh, sorry. We recommend using CPP check, the latest version of CPP check, which is 2.13.4. And here's the steps to install CPP check from the source. So the clone repository and the build steps and adding CPP check to the path. So in the RMM project, we can that this is the command to integrate CPP check with the CMake in the RMM project. And so CPP check has, like, as I said, two variant. We can run CPP check standalone without the MISRA add-on and with the MISRA add-on. So these are the two steps to run it. And it generates an XML output uh, in the build folder. So that's CPP check XML or CPP check MISRA XML in the build folder. And so yeah, this is the manual. And RMM project has a lot of additional flags which we pass on to the CPP check, and we can refer to the manual to go over all those flags. So this is the MISRA JSON we pass on to the CPP check, and here we can customize all the rules we want to run CPP check against. And so the MISRA rules file is we need license to use MISRA rules file. So if you have one, you can copy it to the RMM root directory and use the rule file. So even without the rules file, we can run CPP check. It's able to report all the errors. It's just that you will not get the error message along with the error message which we have in the MISRA rules file. And yeah, so in the GitHub, you can check what all configurations we are doing for CPP check. So yeah, a lot of time if CPP check is reporting any false positives, so we can add suppressions in the code. So yeah, to add inline suppression, that this is the format, adding comments in the code. So so this is the rule, the CPP check rule. And if there are more than one rules you would like to suppress, you can add multiple rules. And if there's a block of code which you would like to suppress, you can add something like a begin and end tag. And so there is also a suppression text file at the root directory. So if you want to suppress a particular rule altogether, you can add it there. Or if we want to exclude certain directories from running CPP check, like the external directory which has external repos, so these are suppressed from the top level there. Yeah. So it generates, like I said, XML output. So this is a format. It will generate error ID, what is the severity and what is the error message, and the location and the line number. This is an additional tool which CPP check provides to generate an HTML output from the XML output. So it's more user friendly, and so this is how we run that HTML tool. using HTML report. You give the XML file and the directory and the source directory. So this generates a list of HTML files, and we can start looking at the index.html to go over the report. Next topic I want to present is the enhancement we have done in the TFA test framework for RMM validation. So yeah, the agenda is to describe what TFA tests are and how we integrated the CCA software stack with it, how to use and how to build it, what's a realm and what's the realm life cycle, and how we are testing PSCI flow with TFA tests, and a bunch of other miscellaneous tests that we have integrated in the TF-TF. So yeah, quickly going over ARM-CCA architecture. So ARM-CCA provides capability to create protected environments called realms, and realm provides confidentiality that any memory and register which is part of realm cannot be accessed or modified by the hypervisor or any other privileged software. So RMM sits at REL2 exception level, and it manages the realms. And the hypervisor can communicate to RMM through RMI calls, and the realms communicate with the RMM through RSI calls. So yeah, and TF-TF is TFA test is a suite of bare metal tests which has been all there, and we use it to validate the TFA and like without having dependencies of the OS. So we have now integrated realm support to TF-TF. So this is how it looks like. So the TF-TF binary sits at non-secure EL2, and the realm payload is loaded at REL1. And these are the current capabilities that currently we support creation of 2 realm payloads, and each of these realm payloads can have up to 8 REC is a realm execution context or a vCPU. So it supports up to 8 vCPUs per realm. And we also support scheduling each of these recs on multiple physical CPUs. And like realm payload is designed such that it is platform independent so that it can be ported across various platforms.
Just one question. I'm curious about the first bullet.
Yes.
A creation of 2 realms and up to 8 REC per realm. Is it some kind of static limitation with TF-TF, or it could extend?
Yeah, it can be extended based upon like the memory layout. So yeah, they are configurable at build time.
That's essentially macros that you can change and.
Yes. Yes.
Okay. Thanks.
So yeah, this is a read the doc links which has all the. Yeah. So this has instructions on how to run the 3-word execution. It has steps to how to build the TFA test, the RMM, and the trusted firmware, and how to run the FVP, all the arguments of the FVP. So basically, this is the build command for the TFA test. We have a flag which says enable realm payload test equal to 1. It generates 2 binaries, the realm.bin and tf-tf.bin, and the realm.bin is appended at the end of the TF-TF bin. So this is how the memory layout is. We have all the loadable sections of TF-TF, and we have reserved a section for the realm image and a pool of memory to be used for realms. And this is like the macro I was talking about. This is like max realm count. We can just modify this macro and increase the number of realm supported. So the limitation is like this memory has to be the first non-loadable section, so that when the TF-TF bin is generated, the realm.bin can be appended at the end of it. So and when this flag is not enabled, the section is of 0 length, so it makes no difference to the TF-TF binary. So yeah, in after build we have 2 different binaries, and post build we do processing and we append the realm.binary to the final TF-TF. Yeah, so coming to the RMI interface. So this is all the RMI commands which a hypervisor or the host can invoke, like discovery of features, memory replication, realm creation, vCPU scheduling, vCPU management, and the memory interface, managing the stage 2 for the realms. So TF-TF is testing all aspects of this, like all these RMI commands. And and this is the RSI commands which can be invoked from the realm payload side. So again, like for the stage 2 management, this is for the stage 2 management. This is for communicating with the host. We have PSCI support and discovery support. And like another aspect is attestation, but this is not currently covered with the TF-TF framework. So yeah, just coming to what a realm and a rec is. So any realm structure is identified by a realm descriptor or an RD. RD will point to each of, like we can, however, how many vCPUs we want to execute. These are the vCPU rec structures it points to. And RTT is the page tables or the stage 2 page tables which the realm manages. So it can be multiple level up to level 3. And so these are all managed, like host manages them with the help of RMI codes. Coming to realm payload cycle. So these are all the stages described in the spec. So we have to create a spec, create a realm, populate a realm, activate a realm, and then run it, and at the end destroy it. So when we create a realm, we have to allocate memory for RD and RTT and delegate it to the realm memory. We have to allocate params, and these are all the RMI calls: RMI realm create and rec create. Rec and auxiliary granules have to be allocated. By populating a realm, we means populating the stage 2 page tables. And we use this RMI call RMI data create to copy the realm image from the TF-TF section through the actual realm memory. We have a shared non-secure buffer which has to be mapped. And this is the final call init repass, which changes the memory to realm memory. And finally, we activate a realm. So all these steps are encapsulated in a helper function in TF-TF, which says create and activate a realm payload. So coming to the framework, we have a bunch of APIs which a host can call and a list of APIs which a realm can call. So anything which is called by the host, helpers are named as host underscore. This is the convention we follow. And all on the realm side, all helpers are realm underscore the function. And there are many helpers like this. Similarly, all the RMI calls are named host underscore RMI, and all the RSI calls are named RSI underscore whatever RSI calls it. And in addition, we have like PSCI, standard PSCI calls, which can be integrated to the realm payload. And if there's anything common which needs to be present for both, we have made sure that it is part of a library, and that library is then compiled to both host and realm, like pauth. Both will need to use pauth, so it's a common library, and then it is compiled for both of them. So yeah, coming to RTT setup, like how the RTTs are set up. So like I said, this is the TF-TF bin, and realm binary is part of it. So when we start running a test, at that time, the realm.binary is copied over to a realm memory at a different location. So the RMI data create call, it does both the things. It will copy the realm binary to the realm memory, and we also have to create the RTTs for it. And there's a non-secure shared buffer which both can access uh, and share data across. So we use RMI map unprotected API to map that shared buffer. So yeah, this is a very high level view of what a test case will look like. So when execution starts bare metal, we enter TF-TF main and with a single CPU on, and a test function starts running. So when we enter a test function at that time, we have to create a realm and copy the realm.binary to the realm memory. And we set up what commands the realm should do, and the arguments we need to pass to the realm we set it in the non-secure shared buffer. And then we say enter the realm. So enter the realm means we start execution in the realm. So all the test cases are compiled as part of single binary, and based on the test command which was passed, then a particular test scenario is executed. So when cold boot starts and in the realm, in that path, we access this non-secure buffer, get the command which we are supposed to run, and execute function that particular test function, and we return the result back again in the non-secure buffer and return to the host. So there are multiple calls, RMI, RSI calls involved, but this is just a high-level view of this is how a test case flow is. So yeah, this is how we have designed the non-secure buffer. This is to share information across the non-secure host and the realm. So this structure is per uh, rec. We have the log buffer. This log buffer is used for realm printfs. So the realm, since it is platform independent, it does not have a UART of its own. So we pass all the print buffers to the host via this shared buffer, and the host prints it to its own to the host UART. So we have in the shared buffer we have different the log buffer, the command, what command the host is supposed to run, and different parameter values and different structures which the test cases use. Yeah. So yeah, this is RMI rec enter call. So rec enter accepts a rec argument and a run argument. So the run argument contains two different structures, the entry flags and the exit conditions. So the while we are entering rec, we can set up different input parameters, different flags, and the rec will be doing those commands. So we can emulate after a data bot, we can emulate this is for data access emulation. We can insert interrupts back to realm, or we can insert an abort back to realm. So these are all the control flags for entry. And when the rec exits, based on the exit reason, it populates different fields in the rec exit object. So like exit can be due to IRQ or FIQ, due to PSCI. So these are all the exit condition all mentioned in the spec. So TF-TF tries to validate all these scenarios, and we have multiple test cases which execute all this and validates entry and exit parameters. So just an example, in the test case, we have, these are the two test cases. This test case creates multiple recs, but all of these recs run sequentially on a single physical CPU. This particular test creates multiple realms, and both the realms are executed parallelly. So coming to PSCI support, we have, so this is how the RMM spec says CPU on sequence should be. So, uh, so like how host can tell RMM or a rec can request CPU on of another rec. So this is all described in the RMM spec, and we have TF-TF test cases to validate this sequence. So in the realm payload where execution starts at RL1, this is the boot flow, cold boot flow and warm boot flow. So execution starts at realm entry point. For each of the rec, we set up different stack for each rec, depending on which rec it is. Then we decide whether it is cold boot or warm boot. So cold boot or warm boot is decided by MPIDR value. So for the primary rec, the MPIDR is 0, and for rest of the rec, it is incremented sequentially. So if it is a cold boot, then we do the cold boot things. We clear the BSS. We do, the realm binary is position independent. So we have to do pi fix up. We do cache invalidations, and we jump to the warm boot path after that. So Arcanet sets up the execution vectors or the other RL1 context we might need. We enable pauth by setting the keys and enabling bit in the control registers. We enable stage 1, and then we jump to realm payload main, which runs infinitely.
So Shruti, we don't enable MMU for realm payload, right?
So right now we don't enable stage 1. That patch is pending. So we do want to enable stage 1 eventually, and right now we have a pending patch for it. So yeah, this is a test case. Just a snapshot of the logs, which says this executes multiple recs and on different CPUs. So these are a snapshot of the log. So any log which says vmid is the vmid for the realm, and this is the rec number 0, 1, 2, 3, 4. So these are the logs saying that each rec is running on its own CPU. And so these are logs from the RMM side. So it says that it has received a CPU on request, and it has received a PSCI complete request. So this is as per the flowchart I described earlier. So we can see TF-TF is exercising all these RMM calls. So yeah, coming to memory management. So the protected realm IP space has so we have realm protected all realm protected IP space have its own state. So repass can be empty or destroyed or RAM. Similarly, the host side, they both have their own view and they both have their own states. So an hepass can be assigned or unassigned, and a repass can be empty, RAM, or destroyed. And the spec says that this is what a valid transition should look like. So only certain transitions are allowed, and these are the RMI calls which will move them from, say, assigned state to an unassigned state, or these calls will change the repass, like RMI set repass. So all these transitions are defined in the RMM spec. And so we have extensive TF-TF tests which goes through this state machine, and we have validate different aspects of it. So yeah, these are the 2 test cases which validate the sequence I showed before. So these are the pass validation test cases. Coming to exception model. So based on the IPA, the repass and the hepass state, the spec defines the behavior. Like if an IPA is accessed which has a repass equal to empty, and we do a data access, it will lead to a asynchronous support. And so these are different behaviors. If we access something outside of realm space, what is the behavior of instruction and data? So this is summarized in the RMM spec, and we have a lot of test cases to validate that. What is the behavior of unprotected SEA, or these test cases try to access something and cause an abort. This is a quick snapshot of these tests, how a realm abort is generated. And from the host side, we return back the ESR and the uh, FAR registers, and the host validates that, okay, the realm generated and a data bot and validates the behavior. Yeah. And again, like we have a bunch of miscellaneous tests for validating architectural behavior, like architecture features like SV and PMU. We have tests for inserting a interrupt back to realm. And we have other security tests which test p-auth faults and whether data independent timing. So we have different tests for architectural features and security features. So yeah, future planning, like we plan to add more tests for coverage, for more coverage of our RMM features. And we do want to optimize realm payload, realm loading. Like right now, each test payload loads its own realm payload. And within realm payload, also, like when we do a data create, we do a data create for the whole realm binary without knowing the actual size. So there are some possible optimizations which we can do for loading the realm payload. And so LPA2 support was recently added in RMM. So we want to add more tests to test LPA2 support in realms, and yeah, enable stage 1 in the realms with and without LPA2 support. And in future, we want to add tests for planes, which is a new upcoming RMM specification, and device assignment. That's all I had. Any questions? Uh, yeah, that's it. I had. Oliver, back to you.
Thank you, Shruti. I guess in the MISC test, you also have
Yes.
coverage for SME, right? Or at least check the context switch from the host to realms.
SME,
Yeah.
SME, I'm not sure. SV, I know there
Yes, there is support for SME as well, which verifies whether the SME related control bits and SME. While entering in SME, there could be a streaming SVE mode, so whether the registers are saved in streaming SVE mode are valid across context switch. Also, yeah, that test is also covered as part of the SIMD test cases that are in TF-TF.
Right, thanks.
Thanks.
In terms of CI, I gather that is only possible in the internal RMM CI, is it?
Yeah, only the RMM CI test this. The TFA site CI RMM is not exercised.
Right, okay. Thank you, Shruti, for this presentation. Is there any other question for Shruti? If not, is there any other TFA or firmware related question if I extend a bit from anyone, as there is some time left? Okay, if none, I will stop the recording.